The late summer of 1944 was the moment when every pilot in the Allied Air Forces began to sense that something was changing. Reports filtered through debriefings and gun camera footage. German fighters moving faster than anything on the Allied side could match. They climbed like rockets, left no propeller blur, and vanished almost as quickly as they appeared. The men who saw them came back shaken. Some called them ghost planes. Others used a name that sounded half-imagined, the jet. At first, Allied intelligence dismissed the stories as exaggeration. Every month the Luftwaffe was rumored to have some miracle weapon, the rocket fighter, the invisible bomber, the anti-aircraft beam. But by August, photographs from reconnaissance flights over Augsburg and Regensburg showed unmistakable evidence. Airframes without propeller hubs, smooth and shark-like, sitting on test strips surrounded by blast shields. The code name that began to circulate through the corridors of Air Technical Intelligence Command was Project Schwalbe, Swallow. The aircraft's real designation was Messerschmitt Me 262. The Allies had known the Germans were experimenting with jet propulsion, but they assumed the technology was still immature. It wasn't. On July 26, 1944, over Munich, 2 P-51 Mustangs of the 20th Fighter Group encountered a pair of aircraft that closed on them at nearly 550 miles per hour, fired a burst, and disappeared before the Americans could react. One Mustang went down in flames. The other returned with gun camera footage that left intelligence officers stunned. The Germans had operational jets, and they were already in combat. From that moment, the race was on, not just to stop the Me-262, but to understand it. Allied scientists had spent years working on turbojet concepts of their own, the British with Whittle's engines, the Americans with General Electric's axial designs, but none had yet reached mass production. The Germans, somehow, had solved the puzzle first. What the Allies needed was a specimen, a captured aircraft, intact enough to study, to dissect, to explain. That chance came only weeks later, almost by accident. On the morning of March 31st, 1945, as the Western Front pushed deep into Germany, a Luftwaffe test pilot named Hans Fay took off from Lechfeld Airfield in a brand-new Me-262A1A. He was supposed to deliver it to a dispersal base near Munich. Instead, seeing the chaos of retreating columns below and realizing the war was lost, he turned west and landed on the first stretch of Allied-held territory he could find, a captured Luftwaffe strip near Frankfurt. When American sentries rushed to surround the strange twin jet, Fay climbed out, raised his hands, and said in broken English, "I bring you the machine. War is over for me." For the Allied engineers who arrived hours later, it was like stumbling on a machine from another world. The aircraft sat sleek and silent in the gray afternoon light, its twin Junkers Jumo 004 engines still ticking with heat. The nose carried 4 30mm cannons. The cockpit bristled with unfamiliar dials. Its skin was a patchwork of aluminum and steel, smooth to near perfection. The men from the Army Air Force's Air Technical Intelligence Command, known as ATIC, could hardly believe their luck. For the first time, they had a Me-262 not wrecked, not burned, but whole. They sealed the field and brought in a recovery team. The aircraft was drained of fuel, its guns made safe, and its dimensions recorded. Within 48 hours, it was crated onto a flatbed truck, bound for the intelligence center at Cherbourg. From there, it would be shipped to England, to a place called Farnborough, the Allied clearinghouse for captured enemy technology. The order was clear: take it apart, learn everything. What followed over the next months was one of the most extraordinary dissections in aviation history. The team assembled to study the Messerschmitt was a cross-section of Allied engineering talent. British specialists from the Royal Aircraft Establishment, American officers from Wright Field, and civilian consultants from Rolls-Royce, General Electric, and Pratt & Whitney. They were not soldiers now, but detectives, standing before an artifact that seemed to rewrite the rules of flight. When the crates arrived at Farnborough in late April, the Me-262 was reassembled inside Hangar 5 under heavy guard. Its lines drew silence, even from men used to marvels. The swept wings, 18.5 degrees back at the quarter cord, were like nothing then flying. The undercarriage was fully retractable, the nose tricycle, the canopy a seamless bubble giving the pilot panoramic vision. Beneath each wing hung the heart of the mystery, the Jumo 004B, one turbojet, Germany's first mass-produced jet engine. For 2 weeks, the engineers examined the airframe without removing a bolt, sketching every contour. They noted that the aircraft's construction was both crude and ingenious. Where Allied planes used precision machine fittings, the Germans had resorted to stamped steel and spot welds. Rivets were uneven, panels mismatched. Yet the overall design was brilliant, built to be assembled by semi-skilled labor in dispersed factories. It was the embodiment of late-war Germany, technological genius fighting industrial collapse. When the first engine was detached from its mount, the room filled with the smell of burnt kerosene and oil. The GMO 004 was unlike anything in Allied service. Instead of a centrifugal compressor, as in the British Whittle design, it used an axial flow layout, air drawn straight through a series of narrowing stages toward the combustion chambers. That design promised higher efficiency and lower drag, but it demanded tolerances that only the most advanced metallurgy could provide. The Germans had achieved it, barely, using chromium-nickel steels and a labyrinth of cooling ducts to keep the turbine blades from melting. When the Allied metallurgists tested those blades, they discovered the secret that defined the entire machine. The Germans hadn't mastered high-temperature alloys. They had simply cheated time. Each engine was built with parts designed to last only about 25 hours of flight. The war had forced them to trade durability for quantity. Every Jumo was, in essence, a disposable masterpiece, just long-lived enough to fight, not to survive peace. That revelation stunned the engineers. The Me-262's performance, speeds of 540 miles per hour, climb rates unmatched by any piston fighter, had not come from some unknown physics. It had come from radical pragmatism, the willingness to sacrifice lifespan for speed. Allied industry, with its focus on reliability and longevity, had never dared such extremes. In that compromise lay the true genius of the German jet program, and the lesson that would reshape aviation for the next 50 years. The British immediately ordered comparative tests. At Farnborough and later at Wright Field in the United States, the capture Me-262s were flown by Allied test pilots under strict conditions. Squadron leader Eric Winkle Brown, the Royal Navy's legendary test flyer, was among the first. His notes were precise, acceleration remarkable, control a high-speed stable, roll rate sluggish, takeoff demanding due to slow engine response, landing hazardous. The jet's engines spooled slowly, producing power only after seconds of delay, a fatal gap in combat if handled poorly. Yet once airborne, it was untouchable. Against it, even the best Allied propeller fighters felt archaic. As more examples were captured from abandoned Luftwaffe bases, the analysis deepened. Engineers stripped fuselages, measured wing profiles, and compared the data to theoretical models. They found that the 262's modest wing sweep wasn't for supersonic flight. No one yet imagined that frontier, but to correct for the shifting center of lift as the aircraft approached transonic speeds. It was a design born of intuition and experiment, not computer modeling. The Germans had discovered, empirically, the beginnings of the aerodynamics that would dominate the jet age. Meanwhile, in the United States, the first reassembled Me-262 took to the skies over Wright Field under the serial number FV-111. American observers watched in awe as it streaked past at speeds their radar scarcely tracked. The test pilot, Lieutenant Colonel Harold Watson, radioed after his first flight. "Now I know what our boys were up against." He added later, "If they'd had fuel and pilots enough, the war might have lasted years longer." But the real treasure was not the speed, it was the understanding. The dissection of the Me-262 taught the Allies more about jet flight in 6 months than years of theory ever had. The axial flow compressor, the annular combustion chambers, the use of tricycle landing gear, and hydraulically actuated flaps, all of it went into Allied design notebooks. The British adapted the data into the Gloucester Meteor's later variants. The Americans used it to refine the Lockheed P-80 Shooting Star and, later, the F-86 Sabre. In that sense, every jet that fought over Korea and beyond carried traces of the German pioneer they had once feared. Yet perhaps the most remarkable discovery was psychological. The engineers realized that the Me-262 was not a miracle of advanced resources, but of desperate improvisation. Germany had fielded the future with tools of the past: low-grade metals, unskilled labor, and airfields bombed to rubble. Its engines were fragile, its maintenance hellish, but its concept was flawless. The jet age had arrived not through abundance, but through necessity. For months, teams at Farnborough and Wright Field continued their forensic work. Every cable, bolt, and instrument was cataloged. The radar range-finding gun sight, a primitive analog computer, was dismantled and replicated. The canopy's framing, designed to reduce glare, became standard on Allied jets. Even the Me-262's flaws, its slow acceleration, its vulnerable engines, became lessons in what not to repeat. The engineers were not just learning from their enemy, they were inheriting him. By late 1946, the surviving Me-262s were distributed to museums and research centers. Some flew under Allied markings, others were stripped for study. The knowledge extracted from them fed into a generation of new designs: the British de Havilland Vampire, the American Republic F-84, and the Soviet MiG-9, all bore its influence. The Germans had built barely 1/400 of the jets, too few and too late to alter the war, but enough to alter history. When the Allied engineers finally finished their reports, they titled them with dry understatement: Evaluation of Enemy Aircraft Type 262, Messerschmitt, Jet-Propelled Fighter. But between those pages lay the birth certificate of the modern age of flight. For the first time, human beings had crossed the boundary between the mechanical sky of pistons and the smooth continuum of the jet stream. They had captured the future, taken it apart, and, piece by piece, learned its secret. When Germany finally surrendered in May 1945, the Me-262s were scattered across dozens of airfields, half-finished or abandoned. Some were intact under camouflage nets. Others lay half-assembled in barns and tunnels. What had been the pride of the Luftwaffe was now the most coveted technological prize in Europe. Within days, Allied technical units were racing each other to capture and catalog every surviving jet. At Lechfeld, Neuburg, and Schwabisch Hall, British and American teams loaded the aircraft onto flatbed trucks. In northern Germany, Soviet detachments moved just as quickly, seizing entire assembly lines before the Western Allies could reach them. It was the quiet beginning of another contest, one that had nothing to do with battlefields and everything to do with the future. Whoever mastered the Me-262 secrets would lead the next generation of flight. The official Allied directive was clear: each power could claim examples of advanced German technology within its occupation zone. But in practice, boundaries blurred. American Air Technical Intelligence Command officers moved east under false liaison orders to secure engines and instruments before Soviet units arrived. The British dispatched rapid response groups to intercept rail shipments of parts heading into the Russian zone. Even the French, who had been largely excluded from jet research during the war, scoured their sector for anything salvageable. It was a scientific gold rush. In June 1945, a special Anglo-American project was established under the codename Operation Lusty, short for Luftwaffe's secret technology. Its mission: to collect, transport, and analyze every advanced German aircraft that could be found. The Me-262 was priority number one. Hundreds of engineers and mechanics followed behind the occupying armies, armed not with rifles, but with clipboards and cameras. They moved through hangars filled with wreckage, identifying engines, blueprints, and jigs. The speed of their operation was astonishing. Within 2 months, more than 200 Me-262 airframes had been cataloged. Some were too damaged to move. Others were in good enough condition to fly. The British captured several at Schleswig and immediately transferred them to Farnborough. The Americans secured another dozen in southern Germany, which were dismantled and shipped by sea to the United States. The Soviets captured the Central Junkers engine plant at Dessau, along with crates of Jumo 004 components and the entire design bureau. In the chaos of surrender, even the engineers themselves became prizes. At the heart of this scramble was a simple realization: the Me-262 wasn't just a fighter. It was a glimpse into an entirely new way of thinking about flight. Its combination of aerodynamic refinement, power-to-weight ratio, and manufacturing efficiency showed that the Germans had reached beyond piston age constraints. To the Allied engineers, the aircraft was a roadmap, not just a weapon. In Britain, the first flights of captured 262s under Royal Aircraft Establishment markings confirmed the performance data. The aircraft's top speed of 540 miles per hour at 20,000 feet remained unmatched by any Allied type. The debriefings from these tests fill hundreds of pages of technical reports, noting both brilliance and flaws. The engine's poor acceleration, the nose-heavy handling on takeoff, the difficulty of maintaining turbine temperature without damage. Yet every fault was instructive. Each limitation told designers where the next generation must improve. The Americans took a different approach. At Wright Field, Ohio, the Me 262s, now redesignated FE401 to FE410, were stripped down to the last rivet. The engineers reassembled one under the guidance of captured German technicians. When it finally flew over Dayton in 1946, test pilots remarked that the experience was both exhilarating and unnerving. The aircraft's smoothness, the whisper of its jets, and the surreal sense of power left an impression that none forgot. Colonel Harold Watson, who oversaw the tests, later said, "The airplane was more than a weapon. It was a prophecy." Meanwhile, the Soviet Union was conducting its own experiments hundreds of miles away. The Red Army had overrun much of the eastern German industrial belt, including the key Messerschmitt plants at Regensburg and Obertraubling. They found warehouses filled with incomplete Me 262s, design documents, and wind tunnel data. Soviet engineers quickly recognized their value. By late 1945, a delegation of German specialists was ordered to relocate eastward, to Moscow, Leningrad, and the secret testing base at Podberezhny. Their task was clear: teach the Soviets everything about the Jumo 004. Among them was Ferdinand Brandner, a brilliant propulsion engineer who would later design the engines for the MiG-15's ancestor, the MiG-9. His team rebuilt the 004 under the name RD-10. Soviet pilots soon took to the skies in a reverse-engineered Me 262 clone designated S-92. It flew with mixed success, unreliable and dangerous, but gave the USSR its first taste of jet combat readiness. The lessons from those flights fed directly into the development of the MiG-15, the fighter that would one day challenge American jets over Korea. Back in the West, similar lines of descent were taking shape. Rolls-Royce engineers, poring over captured 004 blueprints, incorporated several of its concepts into their own axial flow designs. Their new engine, the Avon, would power the next generation of British jets. In the United States, General Electric and Westinghouse drew on both the Me 262 and British Whittle technology to refine their turbojet families. The result was the J-35 and J-47, the power plants behind the F-84 Thunderjet and the F-86 Sabre. Both owed their existence to what had been learned from dismantling Germany's masterpiece. The Me 262's airframe, too, left its mark. Its modest wing sweep, once thought arbitrary, was soon recognized as critical to transonic flight. As Allied aerodynamicists pushed toward the sound barrier, they re-examined the Messerschmitt's geometry and realized that its designers had accidentally discovered the principles of compressibility. This insight would directly inform the North American F-86 and the Soviet MiG-15, two aircraft born from opposite sides of the captured data. The Allied engineers who performed these dissections understood that they were standing at the crossroads of eras. The piston engine and propeller had taken aviation as far as it could go. Beyond lay the domain of pure airflow and jet thrust. The Me 262 had been the threshold, the imperfect prototype of an inevitable future. But there was another aspect of the aircraft that fascinated the investigators: its philosophy of design. German engineers, faced with material shortages and bombing, had been forced to build with ruthless efficiency. They standardized components, simplified structures, and used modular construction decades ahead of its time. Where Allied factories built entire fuselages under one roof, the Germans had scattered subassemblies across the countryside to be joined in underground plants. Every Me 262 was a logistical jigsaw puzzle, and yet it worked. In that dispersed, flexible manufacturing system lay the seeds of what would later be called just-in-time production. The Allied teams documented everything. They photographed jigs, molds, and fixtures. They interviewed surviving German foremen about workflow and quality control. Many of these notes would later resurface in industrial management studies, not in military manuals, but in business schools. The Me-262 had not only changed flight, it had changed the way humans thought about building. By 1946, most of the captured airframes had been moved to research centers. A few were kept flying for demonstrations. The British displayed one at Farnborough Air Show to a stunned public. In the United States, another performed test flights at Muroc Dry Lake, the future Edwards Air Force Base, where the jet age of America would begin. Spectators described the sight of the German plane streaking over the desert as eerie, almost ghostly, as if a relic of the Third Reich had been resurrected to announce a new era. Yet for all the fascination, there was unease. Many of the Allied engineers were aware that the men who had built the Me-262 had done so under a regime of terror, with forced labor and constant air raids. The genius of the machine was inseparable from the horror of its origins. To study, it was to confront that contradiction. They were learning from their enemy, even as they buried his world. Still, the work continued. The more they learned, the clearer the picture became. The Me-262 had not been an isolated marvel, but the spearhead of a broader German vision for air power. Plans recovered from Messerschmitt archives described entire families of jet bombers, reconnaissance planes, and long-range interceptors. Had the war lasted another year, the skies of Europe might have looked entirely different. The Allies' decision to accelerate their own jet programs was, in part, an act of fear of what had nearly been. By the end of the 1940s, the influence of the Me-262 was everywhere. The British Meteor and the American P-80 had already entered service, but the next generation, the swept-wing F-86 Sabre and MiG-15, owed their lineage directly to the captured German research. The jet race that defined the Cold War began in those hangars at Farnborough and Wright Field, where Allied engineers first unbolted the nacelle of a Jumo 004 and looked inside. And yet, for all their analysis, one question lingered among them. How had a nation on the brink of collapse achieved such a leap? The answer was both simple and profound. The Germans had gambled everything on technology. They had diverted scientists, engineers, and scarce resources toward the idea that innovation alone could reverse defeat. It couldn't, but in doing so, they had opened the door to the future. For the Allied engineers, taking apart the Me-262 was not merely a technical task. It was an act of translation. They were decoding a new language of flight, one written in steel and fire, born from desperation, but destined to outlast it. When 1946 turned into 1947, Europe's skies were filled with the ghosts of Germany's collapsed air force. Broken fuselages rusting in hangars, half-buried jigs in mountain tunnels, crates of drawings scattered among ruins. But in laboratories from Farnborough to Dayton, and on new test ranges in the Soviet steppe, those ghosts were coming back to life as blueprints for the future. The Messerschmitt 262 had become the seed crystal around which the jet age formed. In the United States, the engineers at Wright Field called the effort Project Paperclip Air Technical Section. Its brief was simple: gather as many German aeronautical scientists as could be found, bring them to America, and make them work for peace before the Soviets could reach them. Dozens of engineers from Messerschmitt, Junkers, and BMW were quietly flown to Boston and then to Dayton under assumed employment contracts. They were interrogated, debriefed, and then set to work inside new offices of the Air Material Command. Among them was Dr. Hans von Ohain, the physicist whose early patents had laid the groundwork for the Jumo 004's axial flow. He was assigned to analyze American compressor research, bridging the gap between captured German experience and U.S. theory. His presence was controversial. These men had built weapons for Hitler, but the Air Force saw no alternative. The jet era could not wait for morality to catch up. The same calculus played out in Britain, France, and the Soviet Union. Each side convinced itself it was rescuing science from politics, even as it weaponized it again. Britain moved first. The Royal Aircraft Establishment, absorbed the Farnborough Enemy Equipment Division into a permanent jet propulsion department. There, engineers dissected not only the Me-262, but also the later German projects found at Oberammergau, mock-ups for supersonic delta wings and tailless designs. Geoffrey de Havilland's team borrowed heavily from those studies when designing the DH-108 Swallow, and later the Comet airliner, the first jet passenger plane. The Germans had shown that metal fatigue and aerodynamic heating were the new frontiers. The British turned those lessons into commercial flight. In the United States, the influence was even broader. General Electric's engineers, studying JUMO blade metallurgy, realized that the Germans' use of hollow cooling channels could be combined with new nickel-chromium alloys to create turbines that would last hundreds of hours rather than dozens. The result was the J-47 turbojet, an engine that powered not only the F-86 Sabre, but also the B-47 Stratojet bomber, the backbone of early Cold War deterrence. Each blade in that engine carried within its curves the lineage of the JUMO 004's fragility, perfected into permanence. At the same time, the North American Aviation Design Bureau studied the Me-262's swept-wing geometry. Their aerodynamicist, Ed Schmud, pored over the captured wind tunnel data taken from Messerschmitt's Augsburg archives. He noticed that the Germans had measured pressure distribution near Mach 0.8, the regime where shock waves first formed on wings. That data explained why the 262 remained stable when Allied fighters began to buffet at high speed. Schmud applied the same principle to the Sabre's 35-degree sweep, giving it both speed and maneuverability. When the F-86 met the Soviet MiG-15 over Korea in 1950, it was effectively a contest between two aircraft born from the same German research notes. In the Soviet Union, the process was more direct. The engineers from Dessau and Prague had been relocated to the new Design Institute OKB, one under German supervision, but Soviet command. There they rebuilt the Me-262 as the S-92 and its two-seat trainer variant CS-92. The flights were brief, often plagued by engine fires, yet each sortie produced reams of data. The Soviets learned the practical realities of jet operation, the need for long runways, careful throttle control, and new lubricants resistant to heat. From those lessons, Artem Mikoyan and Mikhail Gurevich drew their conclusions. By 1948, their prototype I-310, soon to be known as the MiG-15, took shape, powered by a British-licensed Rolls-Royce Nene engine, but shaped by German aerodynamics. In Moscow's air shows of the early 50s, its silhouette looked eerily familiar. Swept wings, tricycle gear, twin-barrel nose cannon. The Me-262 reborn in red stars. To the engineers who had dismantled the original, this outcome was both inevitable and unsettling. The machine they had studied in hangars under Allied guard had become the blueprint for two opposing superpowers. It was as though the 262 had transcended nationality, becoming the lingua franca of post-war flight. Back at Farnborough, the surviving captured jets were slowly retired. One was sent to the Smithsonian, another to Cranfield for instructional use. Yet their influence lingered in every design meeting. Engineers quoted the German blueprints the way theologians quote scripture. Remember the 262's intake shape, they would say when arguing about new compressor ducts, or check the German sweep angle when drawing experimental wings. The Messerschmitt had become the yardstick by which progress was measured. The broader philosophical shift it triggered was even more profound. Before the war, aircraft design had been an art, trial, error, and intuition. The Me-262 proved it could be a science of systems. Jet propulsion demanded precision in metallurgy, fuel chemistry, and aerodynamics far beyond the rule-of-thumb methods of the 1930s. The Allied engineers who studied it realized that aviation would henceforth belong to laboratories as much as to airfields. Post-war institutions like Britain's Royal Aircraft Establishment, America's National Advisory Committee for Aeronautics, and the Soviet Central Aerohydrodynamic Institute all expanded directly in response. Each traced its urgency to the day the first captured Me-262 arrived on a flatbed truck. By 1949, jet research had become the central theater of the new Cold War. The weapon that had arrived too late for Hitler now defined the balance between superpowers. Every advance, the first supersonic flight, the first jet bomber, the first guided missile, stood on the shoulders of the engineers who had once walked around a silent, burned-out Me-262 in a Farnborough hangar, wondering how it worked. The paradox was unmistakable. The Allies had defeated Germany's jet squadrons, yet they inherited its dream. The men who had taken apart the Swallow had given the world wings it could never again take back. By the dawn of the 1950s, the jet engine had shed its wartime uniform. The sound that had once meant danger now promised speed, comfort, and modernity. Newspapers called it the sound of the future. But for the engineers who had spent nights inside hangars dismantling the Messerschmitt 262, that sound carried another meaning, proof that their long study had borne fruit. The transition from warplane to airliner began in Britain. There, the Royal Aircraft Establishment's Jet Propulsion Department and de Havilland engineers sought to adapt what they had learned from the Me-262 and other capture designs to peaceful use. The result was the de Havilland Comet, the first commercial jet airliner. Its clean, swept wings, buried engines, and pressurized fuselage were the culmination of research that had started the day British technicians first looked inside a Jumo 004. Many of the aerodynamic corrections applied to the Comet's wings, particularly the distribution of lift at high subsonic speeds, came directly from German data seized at Göttingen's Aerodynamic Research Institute. What had once guided the Me-262 into combat now guided families across continents. The Americans followed with their own giants. At Boeing and Douglas, engineers who had studied Me-262 and AR-234 structures applied the same metal fatigue lessons to civilian prototypes. The Boeing 367-80, the prototype that would become the 707, owed part of its stability to airflow mapping techniques originally developed in Messerschmitt wind tunnels. Even the jet's engine placement, underslung and streamlined nacelles, reflected conclusions drawn from post-war testing of captured German configurations at Wright Field and Muroc. The ghosts of Augsburg and Lechfeld were now flying beneath the corporate logos of Pan Am and TWA. Behind the scenes, many of the minds that had once sketched the Me-262's blueprints were working again, but this time under different flags. Some, released from Allied internment, joined the newly founded companies of West Germany's reborn aerospace sector, Messerschmitt Boeing, Dornier, Heinkel. Others emigrated, quietly hired by British and American firms seeking experience no university could teach. They brought with them habits formed during the war: modular design, standardized fittings, field-replaceable components. Those habits became the grammar of modern manufacturing. At the same moment, governments institutionalized what the wartime engineers had done ad hoc. The United States created the Air Research and Development Command in 1950 to coordinate scientific advances across industry and military. Britain established the Ministry of Supply's Aircraft Production Division, and France rebuilt its own Aerospace Research Bureau using documentation seized from Messerschmitt's archives. Everywhere, the same realization had taken hold. The future of flight was too complex for any single company or nation to manage without shared data. Collaboration, once forced by war, became policy in peace. The Me-262's influence also reshaped pilot training and safety. Its notorious throttle lag and fragile turbines had taught early jet pilots the value of restraint and procedure. Manuals for the first generation of civil jets repeated warnings that read almost word for 1945 test reports. Avoid rapid throttle changes below 5,000 feet. Allow engine spool-up time before climb. The lessons learned in battlefields and captured hangars became aviation law. In West Germany itself, the aircraft remained a phantom until the mid-1950s. Under Allied restrictions, jet development was banned. Former engineers could only consult abroad. But when the ban lifted in 1955 and the new Luftwaffe was formed, the first jets it received, the Canadair Sabre and later the Lockheed F-104, were spiritual descendants of the Me-262. Veterans who had once fought in it now trained pilots to fly its offspring. The circle had closed. By then, the rest of the world had accepted that the Messerschmitt's legacy reached far beyond military design. Its lessons in airflow and metallurgy informed everything from high-speed trains to gas turbines. Even NASA's earliest supersonic studies cited German wind tunnel data, captured in 1945, as foundational. The engineers who had once stood around a dismantled Swallow realized that they had not merely studied an airplane. They had touched the hinge of technological history. In the cultural memory of aviation, the Me 262 became a paradox. To pilots, it was both marvel and menace. The machine that had promised victory to a doomed regime, but delivered progress to its enemies. Museums displayed its smooth, predatory shape as a warning and as a milestone. Historians debated whether its influence was exaggerated. Engineers knew it was not. They could trace the lineage of every jet nacelle and every wing sweep back to that captured airframe. By the early 1960s, when the jetliner became the emblem of a shrinking planet, few passengers sipping drinks at 30,000 feet knew that their journey owed anything to a desperate wartime invention. But the engineers remembered. The men at Rolls-Royce still kept a Section Jumo 004 in a glass case. At Wright-Patterson, the U.S. Air Force Museum displayed a restored Me 262 beside the Sabre, the child and parent reunited. And at Lechfeld, where the first operational jets had taken off 2 decades earlier, new German Air Force trainees studied aerodynamics in classrooms built on the old runways. The message those instructors gave their students was the same one Allied engineers had written in their 1946 summary reports. Progress itself is neutral. What matters is who guides it. The Me 262 had proven that brilliance and ruin can coexist in a single machine. Out of its shadow came the brightest century of flight humanity had ever known. By the end of the 20th century, the sound of a jet engine was so ordinary that few people remembered a world without it. Yet for the generation of engineers who had first stood beside a silent Me 262 in a captured hangar in 1945, that sound was the echo of a revelation. They had seen, with their own eyes, the moment when humanity left the propeller age behind. Every turbine that whined to life afterward carried within it the ghost of that machine. For historians, the Me 262 was more than a weapon or a milestone. It was a case study in how innovation emerges from crisis. The German designers who built it had worked under bombardment, short of materials, driven by a regime in collapse. Their success proved that desperation can accelerate discovery, but at a terrible cost. Allied researchers studying the aircraft after the war began to see that paradox clearly. The jet age, they realized, had been born not out of prosperity or peace, but out of the final convulsions of a world at war. In the archives at Farnborough and Wright-Patterson, the thick binders of reports remained for decades, labeled Evaluation of Enemy Aircraft. Within their pages lay the story of how the future was reverse-engineered from defeat. Metallurgists noted the composition of turbine blades. Aerodynamicists plotted the lift curves of the swept wings. Economists later traced the lineage of modern manufacturing back to the modular, dispersed production that had built the Me 262 under Allied bombing. The aircraft had quietly reshaped disciplines far beyond aviation. In the Cold War years, its descendants filled the skies. American F-86 Sabres, Soviet MiG-15s, British Hunters, French Mystiers, all bearing, in their proportions, the unmistakable DNA of the German jet. The men who flew them often never knew. But the engineers who designed them remembered every rivet, every airfoil contour they had measured from that captured Swallow. By the 1970s, as aviation historians gained access to declassified files, the full picture emerged. The Me 262's revolutionary step was not simply its engines or its speed. It was the integration of systems. It was the first aircraft conceived entirely around the jet principle rather than adapted to it. Its designers had rethought everything: airframe, control surfaces, fuel systems, landing gear, to serve one purpose: to move faster than the air could comfortably allow. In doing so, they had opened the door to all that followed: supersonic flight, space planes, guided missiles. The boundaries had shifted forever. Engineers who visited the surviving examples in museums often described a strange mixture of awe and melancholy. The metal looked handmade, almost primitive, yet the lines were modern. The cockpit was cramped, but the layout anticipated the logic of later fighters. To walk around, it was to see the 20th century compressed into one object, half relic, half prophecy. Some called it the first true aircraft of the modern world. The moral question never disappeared. The Me-262 had been built for a criminal regime, and its deployment had prolonged suffering. But history rarely allows inventions to choose their masters. The jet itself was neutral, a tool shaped by human intent. Allied engineers had proven that by transforming it from an instrument of war into the foundation of peace. In the classrooms of aeronautical universities from London to Los Angeles, professors taught its principles stripped of ideology. Lift coefficients and compressor ratios replaced propaganda. Knowledge had outlived politics. By the turn of the century, only a handful of original Me-262s remained airworthy. Restorers in Germany and the United States built faithful reproductions using surviving WWII engines and modern alloys. When one of them flew again in 2005, over the same Bavarian fields where the first prototypes had taken off, spectators described the moment as eerie. The jet's whistle, the same sharp note that had terrified Allied bomber crews, now sounded like nostalgia. The Swallow had returned, not as a weapon, but as history remembering itself. Museums around the world began to place the aircraft at the center of exhibits about innovation under pressure. At the Smithsonian, curators displayed it beside the P-51 Mustang to show the contrast between the perfection of the piston age and the raw leap of the jet. In Berlin's Deutsches Technikmuseum, visitors could stand beneath its wings and read the names of the factories where each part had been made, many by forced laborers. The exhibit's message was sober. Genius divorced from conscience is never progress. The machine that had once symbolized German technological pride now served as a reminder of the responsibility that accompanies discovery. Meanwhile, aerospace engineers continue to cite it as the origin point of their field. In lectures on aerodynamics, the Me-262's 18.5-degree sweep was still used as the classic example of pre-supersonic correction for compressibility. In turbine engineering courses, the WWII-004's primitive cooling system was discussed as the ancestor of modern blade technology. In design philosophy, its modular production lines were recognized as the precursor of global manufacturing networks. The Swallow had become both textbook and warning. Historians sometimes called it the machine that closed one century and opened another. It ended the era of visible motion, the blur of propellers, the rhythm of pistons, and began the era of invisible speed, where power came from air itself. When the Allied engineers first watched their captured jet lift off from Farnborough in 1945, they were witnessing that boundary being crossed. One of them later wrote in his diary, "We saw the shape of tomorrow rise from yesterday's ruin." That sentence, rediscovered years later, became the inscription on a memorial plaque at Wright-Patterson Air Force Base. It commemorated not the plane, but the men, Allied and German alike, who had built, studied, and understood it. For without their curiosity, the knowledge contained in that wreck might have been lost to history. Instead, it became the foundation of everything that followed. Today, when airliners trace white lines across the stratosphere and spacecraft re-enter the atmosphere on jets of plasma, the lineage is clear. The Me-262 was the first to confront the sky as a medium to be conquered by heat, pressure, and precision. Every modern engine carries the same logic that Allied engineers uncovered when they pried open its nacelles. Compression, combustion, thrust, a controlled storm. They did not just take apart a German fighter. They took apart the limits of flight itself. In the end, that is the true secret they discovered. It wasn't hidden in its blueprints or alloys. It was the realization that technology, once imagined, cannot be uninvented. The jet was inevitable. The Me-262 had simply arrived first, blazing a trail that others would follow for generations. Its creators had reached for victory. They had given the world velocity. And long after the war that birth had faded into memory, the Swallow still flew, its shadow stretching across every runway where a jet engine roared to life, reminding the world that even in ruin, discovery endures. After 1945, the Allied obsession with German technology didn't stop at jets. The dismantling of the Messerschmitt 262 had revealed a new vocabulary of design, And once engineers learned to speak it, they began hearing its echoes everywhere. The jet's turbines were cousins of rocket engines. Its swept wings foreshadowed ballistic shapes. The Swallow, they realized, had been part of a wider German project, a search for velocity itself. When the United States launched Operation Paperclip, its first objective had been the V-2 rocket program at Piedmont. Yet among the boxes of rocket parts came stacks of Messerschmitt and Junker's aerodynamic research, high-Mach pressure charts, supersonic airflow diagrams, calculations for conical intakes. The same minds who had refined the 262's airflow had also contributed to the V-2's guidance fins. Those documents crossed the Atlantic with Wernher von Braun's team and were cataloged at White Sands, then at Huntsville. In those technical drawings, NASA's future engineers later found the mathematical seed of spaceflight. At Wright-Patterson Air Force Base, the Air Research and Development Command compiled everything under a single heading: German Aerodynamics, 1939 to 1945. Thousands of reports, each stamped secret, captured enemy document, described experiments in supersonic tunnels that the Allies had never imagined possible. One report, written in January 1945 by a Messerschmitt mathematician, outlined the effects of shock waves on a swept wing passing Mach 1.05. It was, in essence, the first modern paper on transonic drag. When NACA engineers at Langley later compared it with their own X-1 test data, they were stunned. The Germans had reached the same conclusions 2 years earlier using hand-drawn graphs and intuition. From those papers came the next leap, the American X-plane series. The Bell X-1, the first aircraft to break the sound barrier, shared with the 262 the same faith in calculated risk, the willingness to design beyond the known. Chuck Yeager's flight in 1947 was the sonic echo of lessons first whispered in the workshops of Augsburg. The British and Soviets reached similar frontiers with their own experimental jets, each tracing the same invisible lineage back to the Swallow. The jet's philosophy, modularity, experimentation, iterative testing, also shaped the new field of guided missiles. When Allied intelligence opened the files of the Luftverteidigungsanstalt in Braunschweig, they found aerodynamic tables for swept-wing projectiles that would later appear, almost unchanged, in early cruise missile research. Even the placement of control surfaces on the U.S. Matador and Soviet KS-1 Kometa derived from Messerschmitt prototypes. Engineers who had once disassembled the Me 262 now oversaw these programs, carrying forward its principles under new banners. Inside factories, the war-borne manufacturing methods of the 262 quietly revolutionized industry. The Germans' practice of breaking assembly into submodules, wings, engines, fuselage sections produced separately and joined later, became the template for post-war production lines. Boeing's 707, Britain's Comet, and the Soviet Tu-104 all used similar modular construction. The just-in-time logistics later perfected by Japan's Toyota system traced its ancestry, in part, to the dispersed production networks that had once hidden Me 262 parts in forests and mines. A method born of survival became the grammar of efficiency. By the 1960s, the Me 262's DNA could be found in places its creators could never have imagined: in nuclear research reactors cooled by jet-style compressors, in gas turbine power plants, in high-speed trains whose nose cones mimicked swept-wing aerodynamics. The Swallow had escaped its category. It had become a principle of motion. Yet among historians, debate persisted. Was the Me 262 truly the first operational jet, or merely the most famous? Britain's Gloucester Meteor had entered service earlier, they pointed out, but the distinction missed the point. The Meteor was a refinement of existing ideas. The 262 was a rupture. It changed the trajectory of every design that followed, not because it flew first, but because it flew differently. It proved that an aircraft could be conceived entirely around thrust rather than lift, that the sky itself could be treated as a continuum to be shaped, not resisted. That mental shift, the transition from flying through air to flying within it, was the jet age's real birth. As archives gradually opened, the human story behind that shift resurfaced. In post-war Germany, surviving Messerschmitt engineers formed alumni associations, trading letters with their former Allied counterparts. They discussed metallurgy, airflow, even mutual respect. Some had met again decades later at conferences on high-speed flight, standing side by side beneath museum displays of the aircraft they had once studied from opposite sides of the war. One British veteran wrote afterward, "We all served different masters, but the machine we pursued was the same. We chased understanding." By the 1970s, television documentaries brought the Me 262 back into public consciousness. Viewers were astonished by its sleekness, its audacity. Interviews with test pilot Hans Fay, the man who had surrendered his jet to the Allies in 1945, revealed the human dimension of that turning point. "I knew it was the future," he said softly, but the war had no future left. His defection, once a footnote, became the symbolic hinge on which technological destiny had swung. The aircraft's surviving examples became pilgrimage sites for engineers. At the Smithsonian's restoration hangar, young aerospace students studied the curvature of its wing roots, running their hands over rivet lines laid down before they were born. In Munich's Deutsches Museum, visitors lingered before the section Jumo 004, reading the tiny numbers etched on each blade, tolerances measured in fractions of a millimeter, achieved without computers. Each part testified to human will at its limit. Meanwhile, new analyses of wartime records uncovered another legacy: data ethics. Many of the aeromedical and performance studies conducted by the Third Reich had used unethical human experiments. Allied scientists after the war faced moral choices about what to do with that information. The contrast with the Me 262's purely technical brilliance was stark. It reminded the scientific community that knowledge is never isolated from the conditions of its creation. Out of that reckoning emerged new international codes on research ethics, unwritten descendants of the same war that had produced the jet. By the 1980s and 1990s, as Germany reunified and aviation entered the digital age, the Swallow's image reappeared not as a threat, but as heritage. Restorers built flyable replicas using modern materials but original blueprints. When one of them took off from Moshing Airfield in 2005, engineers from a dozen nations watched. The sound was identical to the recordings from 1944, a rising metallic howl that turned into a pure, sustained note. The spectators were silent until it landed, then applauded, not for the regime that had built it, but for the audacity of human invention. For contemporary aerospace historians, the Me 262 became the archetype of the transitional machine. It stood at the boundary between two technological epochs, embodying both the limitations of one and the promise of the next. Its imperfections, the fragile engines, the throttle lag, the poor low-speed control, were not failures but growing pains of species learning to run after centuries of walking. Every flaw was a forecast, and still, its legacy expanded. Computational fluid dynamics programs of the 2000s validated many of the flow patterns the Messerschmitt team had only guessed at by instinct. Digital models showed that their wing design, within a few percentage points, predicted the same pressure distribution confirmed by modern supercomputers. What had been intuition under fire turned out to be near-perfect science. The Me 262's ghost continued to surprise the living. The aircraft's story, once confined to engineering circles, gradually entered cultural history. Scholars began comparing it to the atomic bomb and the computer, technologies that compressed decades of progress into a single leap. All three, they argued, were born from the same crucible, a global war that forced humanity to think beyond its own safety. In that context, the Me 262 symbolized not Germany's superiority, but civilization's threshold moment. The future had been invented under duress. Even in popular imagination, the Swallow retained its dual identity. Filmmakers used its image to signify both menace and beauty, the sleek line of evil ingenuity, the elegant silhouette of modernism. Artists painted it as a bird of steel caught between storm clouds and sunlight. It became a metaphor for technology itself, capable of lifting humanity or destroying it, depending on who held the controls. Today, at air shows, when a rebuilt Me 262 streaks overhead, audiences feel a strange mixture of awe and unease. Children cover their ears, veterans look up with tears. The announcers tell the crowd that they are hearing the sound that changed the world. And for a moment, history collapses into a single sensation, the howl of air torn apart by invention.